You have fallen into Event Horizon with John Michael Godier. For today's discussion on possible organics found on Mars, John is joined by Dr. Kevin Hand, a planetary scientist and astrobiologist at JPL, who works on numerical modeling and laboratory investigations concerning the physics and chemistry of icy moons and ocean worlds in the outer solar system. He was a scientist aboard James Cameron's 2012 dive to the bottom of the Mariana Trench, and he was part of a 2003 expedition to hydrothermal vents in the Atlantic and Pacific Oceans. He has made 9 dives to the bottom of the ocean.
Dr. Kevin Hand, welcome to the program.
Thank you.
Now, Doctor, we have a very, very intriguing discovery with the Perseverance rover on Mars, where we have a very unusual rock. Could you give us a profile of this rock and why it got your interest in the first place? In other words, what made you go drill into it?
Before we get to the rock, it makes sense to provide some context of where the rover is right now, because part of what motivated us to investigate this rock is not just the appearance of the rock itself, but also where this rock is, what the context for this rock is. And by that, I mean the following. First and foremost, the Perseverance rover landed in an ancient crater on Mars, Jezero crater, that we have good reason to believe was once filled with water. And the evidence for that comes from this delta, this package of sediments that were laid down at the mouth of a river that feeds into the crater. And the river that feeds into the crater cuts through the crater rim and extends out to the west from what was once a beautiful river valley and lake. And so Perseverance right now is nestled in this dry riverbed in that river valley where water once flowed and cut through the crater rim of Jezero crater and fed into that large lake of Jezero billions of years ago. So that's the context for this rock. What about this rock in particular? Well, we saw this rock, or not this specific rock, but we saw this region of rocks from quite a far distance away as Perseverance was gradually making its way along the southern rim of the river valley. We could look across and see some bright rocks at the bottom of that riverbed. And we gradually made our way there and started investigating these rocks. And sure enough, they appear to be very fine-grained, perhaps sedimentary rocks that may have been laid down in slow-moving water billions of years ago. Now, I'm using a lot of, I'm qualifying my statements there, and I will continue to qualify my statements with maybes and perhaps, because all of this data is very fresh and new. And so it's important to appreciate that a lot of what I'm saying could change as we have more time to investigate the data. But basically, we think we're looking at some rocks that at one point may have been sedimented out of an ancient riverbed.
Now, early in the game, it's important to note that this discovery is like within days of recording this. And this is just hot off the presses type stuff. Now, determining if it is a sedimentary rock. So how do you do that? In other words, can you chemically look at that thing and say, oh, there's only one way that this is going to, and we know Mars has sedimentary rocks. We've known that from other rovers. But establishing if this one is one seems to be important in trying to determine what we're actually looking at here. So how do you tell? How are you guys going to figure that out?
Yeah, well, ultimately to figure it out, we'll have to get these samples back to Earth where we can examine them in great detail and understand the structures within the sample and the chemistry within the sample. But just on a first pass, as on Earth, a key indicator of sedimentary rock, sedimentary structures is layers. And we do see layers within these rocks. And just to add some names to what we're looking at, the region that we've been investigating on Mars within Jezero crater is called Neretna Vallis. That's the valley. And the specific rock region that we've been investigating is called Bright Angel. And then the specific rock that we've been investigating for the past couple of weeks, past few weeks, is called Cheyava. And Cheyava, once we started looking at it up close, we could see that it has these curious spots on it. And the team, just for shorthand, began referring to these as leopard spots because they do look like sort of complicated spots where there's a bright center, a kind of dark rim, and then there's a surrounding matrix material. And when we analyzed these spots with the chemical analytical tools that we've got on the rover, the Pixel instrument and the Sherlock instrument, it was revealed that there are some iron phosphates. And then once we really got beneath the surface, once we abraded the Cheyava rock with an abrasion that we call Apollo Temple, we were able to discern that along with some interesting mineralogical chemistry, there also appears to be a pretty robust signature of organics or carbon compounds within the rock. So that, of course, is tremendously exciting. When we think about the search for life beyond Earth, it's all about seeing if we can check the box on the keystones for life. Liquid water, the elements needed to build life, and some form of energy to power life. Given that this rock is in a river valley, we think we can check the box on the availability of liquid water at some point in the past. Given that we have some robust data now indicating carbon compounds, that's indicative of some of the essential building blocks for life. And we also have indications of sulfur and phosphorus and iron and a lot of the other elements that are essential for building life. And then with the mineralogical analyses that were conducted with the X-ray fluorescence spectrometer, the Pixel instrument, we have indications that the mineralogy includes reduced minerals and oxidized minerals. There's a lot of detail and redox gradients and things like that that we can or cannot go into if you like. But the long and the short of it is you can think of the rocks present at this site as containing some stored geochemical energy, not entirely dissimilar to the kinds of energy that gets stored in batteries, where you can discharge the chemistry of a battery and get work done. Well, life as we know it utilizes energetic reactions in the environment to do the business of life. We can extract energy from our surroundings, and the minerals at Bright Angel within Cheyava rock indicate that these minerals may have been able to help power life.
And that's interesting in itself because if this rock were on Earth, the microbes would like it, or at least the conditions that formed it. And when you see that on Earth, rocks that show fossil traces, not really fossils, but traces, sort of look like this rock, right?
Well, yeah, you can, perhaps we're looking at evidence of a past hot spring or some sort of hydrothermal fluid coming up through fractures, some way in which hot, perhaps even salty water ran through these rocks. And perhaps that mixed with river water, or perhaps one came before the other. We just don't know quite at this stage what the sequence of events was. But there again, that's part of the story that we'll be able to tell once we get the sample back down on Earth.
Now, time frame. How old is this rock? When is this thought to have happened?
Yeah, that's a great question, John. And the here's another reason we need to get our samples from Mars back to Earth. Traditionally, we as planetary scientists and astrobiologists, the way we date a surface, be it the moon, Mars, Mercury, asteroids, Europa, Enceladus, and so on and so forth, is we do crater counts. We create histograms of various sizes of craters. And with that, we can tell a story about a time in the past when there was a lot more debris in the solar system that could have created craters, and more recent times when there's not nearly as many rocks and stuff swirling around, where far fewer craters are created. So the number of craters generally decreases through time. There's some caveats to that, but we've been to the moon, we've collected samples on the moon, and we can age date the moon with the samples that we've collected from the moon. And that helps us tether the cratering impact record on the moon to actual rocks we've collected. Everything beyond the moon, for the most part, is an extrapolation from the moon. So on Mars, we do this age dating in Jezero crater and elsewhere. And I think the latest bracketing of age dates is something like several hundred millions of years, plus or minus. Meanwhile, with a sample collected from Mars and brought back from Jezero crater, we'll be able to refine that dating down to plus or minus roughly 10 to 20 million years. So an incredibly much more precise and accurate dating of exactly when this river flowed on Mars, when the Jezero crater was full of water, at what point did various sediments get laid down, lava flows and ash flows arise and overprint various things. So aside from our search for signs of past habitability and even possible life on Mars, our samples from Mars will help us unravel the story of Mars as a planet and its history in the evolution of our solar system.
I think the Mars sample return mission is obviously crucial, especially now. Especially now. We want to get a look at that rock because that's very intriguing. What's that looking like? Is it, I know that we're running into some problems in questioning the future of the Mars sample return mission, but what is at least the plan to get them back here?
Yeah, so all of the strategic side and all that, that's above my pay grade. So I'm not going to go there in terms of speculation about what will actually happen. But suffice to say, this has been in getting rocks back from Mars to study the history of Mars and the possibility of life having once been on Mars has been part of NASA's planetary science effort for decades. It's a very exciting prospect, and I hope we can get it done sooner as opposed to later. Technologically, what does it actually look like? Well, how it will be done remains to be seen, but at least past architectures have involved some variation on the following. You have a lead rover like Perseverance that has the capability to study the rocks, drill into the rocks, and then collect cores from the rocks. And so as Perseverance has been rolling through Jezero crater, up the Jezero crater delta and into the river valley in which we now reside, we have been collecting these cores and storing them in the belly of the Perseverance rover. We did also drop off kind of a backup cache of samples down at the base of the delta. That was just in case, heaven forbid, something happens. There's a backup cache of cores that a future mission could go after. Then, at least in one of the architectures, another spacecraft comes down. There's a handoff of the core samples to that spacecraft. It then has a configuration where it can launch those samples into orbit around Mars. That spacecraft with the core tubes rendezvous with an orbiter. Once that rendezvous is complete, that spacecraft gets sent back to Earth. And then in at least one of the architectures, the capsule comes careening back to Earth and lands, I believe, somewhere in the desert of Utah, where it's collected with people all dressed up to make sure there's no contamination, and it's brought back to a laboratory. And after that, subsamples are distributed to many of the best laboratories on planet Earth to investigate the samples in great detail.
Yeah, and it pays to remember that although we have meteorites that have an origin on Mars, they're contaminated.
Mm-hmm.
They've been sitting in Antarctica for presumably a very, very long time. And here we would have pristine samples. Is there any plan, though, on doing an atmospheric sample and returning it back? In other words, capture some of Mars's air,
Yep.
for lack of a better term, and get that back here and take a good look at it. Because remember, there was that weird Viking labeled release experiment in the distant past.
Yeah, you got a good memory. So we've already collected an atmospheric sample, and that's part of the inventory. So you're spot on.
It'd be interesting to see what the close up, what the methane and that sort of thing looks like on that planet. Very, very close up. Because as you know,
Yeah.
I don't know that it was Perseverance that did it. I think it might have been Curiosity. It was detecting just interesting wafts of methane
Mhm.
that just was seemingly just coming out of nowhere. And you got to wonder about things like,
Yeah.
how volcanically active is Mars? What's left? And these other questions. And then, of course, life, So it's very intriguing. And I'm hoping that we can really get that sample return mission not only going, but in full gear and get it back as quickly as we can without actually having someone going there, some human standing there and picking them up and returning them themselves.
Yeah. Well, and you're absolutely right. So that methane, that whiff of methane, that measurement was made by the Curiosity rover, and it's a head scratcher. And much of what I've been talking about so far is our search for signs of past life on Mars, life as preserved in the ancient geologic record. These rocks that are billions of years ago. But that methane signal, who knows? Maybe it's, as you mentioned, volcanic in origin, some sort of geologic activity still occurring on Mars. Maybe it has, some connection to subsurface life. We just don't know. But in that context, it's important to remember that for all we know, the subsurface of Mars could still be active with volcanic activity or other kinds of activity, and that may contribute to this confusing methane signal.
Though that alone is interesting because Mars is better preserved than Earth. Earth likes to resurface itself and weather away and subduct and all this stuff. Whereas Mars almost looks like a fossil in its
Hmm.
own right.
Yep.
And it's preserving information from a much earlier time in the history of the solar system. And this is a key time for Earth where you get to see things a little bit differently. And most importantly, there is abiogenesis
Mhm.
because any evidence we have on Earth for what exactly happened there is gone,
Mhm.
long gone. We've got maybe some zircon crystals or some things that show evidence of early life, but we got nothing for the most part. Whereas Mars may preserve more if indeed it did once have life. Wouldn't you agree?
Absolutely. And as you mentioned, on Earth, our wonderful plate tectonics and water cycle has erased much of the evidence of what we call the Archean rock record. You have to go to Australia, South Africa, Greenland, parts of Canada. There's just not that much of that ancient rock record on Earth left for us to explore in sort of the unaltered, pristine state, whereas Mars may well have quite an abundance of that. Now, that gets at the question that is a question at the heart of just about everything I do, be it Mars or Europa or Enceladus, et cetera, and that is the origin of life easy or hard? And on Mars, as you well appreciate, once upon a time, it had not just flowing water in Jezero crater and the Retinivalis, but the evidence points to a wet and warmer Mars, a Mars that was a sister planet to Earth, perhaps overlapping in time and somewhat proximity in space as a habitable world with possible inhabitants. And so, were we to find evidence of past life on Mars, the follow on question is then, is that evidence of life that arose on Mars, that began on Mars, or is it somehow connected to life on Earth and maybe an asteroid or comet hit Earth and ejected ancient microbes and transported them to Mars, or vice versa? And that's a really important question to consider in the context of how many times in our own solar system might the origin of life have occurred?
Is it easy or is it hard? Now, that is the key question. And that is something that I've actually find. I love SETI. I support SETI wholeheartedly, and I think we should continue to look for radio signals and technosignatures and everything else. But I don't know that we're going to find it or find it within any amount of time I'm going to be here. But I think within my lifetime, say give it another 40 years, I think we have two ways to crack abiogenesis. We either find it, Mars or Europa or Venus, something that we can prove is a second occurrence, or it'll happen in the laboratory and the abiogenesis chemists will say, look, this is easy or it's very hard. And that answers the question, because if it's easy, there are microbes everywhere pervading the universe, and you can expect them everywhere. But one thing that intrigues me most about this star system is the fact that it had 3 surface ocean worlds. 2, possibly 3, perhaps I should say. We know Mars, we know Earth, Venus probably. That's an awful lot of water worlds for one star system. And it seems to me that would indicate, if we could really establish that Venus had it, that would indicate that Earths are very common in the Milky Way galaxy. Is that correct, or could there be something weird going on?
All of the above. So the exoplanet studies to date show that Earth-like planets are not as rare as we once thought they might be. One of the big questions in planetary science right now is how solar systems evolved through time, what kind of dance and reconfiguration occurs with giant planets like Jupiter. Do they get formed close in and migrate out, or get formed far out and migrate in? What kind of dance and ejection process happens throughout those early days of solar system evolution? But nevertheless, using our own solar system as an interesting template, I think the question, as you know, really does arise of making sure that we consider not just what's happening at a given planet right now, but what the planetary evolution of that planet and other planets in that solar system looked like. Because you're absolutely right. At one point in time, perhaps a couple of billion years ago, maybe 3.5. Again, the boundaries on this are not particularly well constrained. But there may have been a time when Venus, Earth, and Mars had liquid water environments and could have hosted life, with, again, the caveat if the origin of life was easy. Now, to your point about SETI and solar system exploration, I agree entirely. I used to work for the SETI Institute, love the SETI Institute. I hope that we find a signal, be it radio or optical or otherwise. But one thing that I do take heart in is that, at least when it comes to exploring our solar system, that is something deterministic that we can engage in. If we so choose, we can commit to building the spacecraft, building the instruments, launching these spacecraft, and getting these missions out there to explore these worlds, to potentially answer this age-old and profound question of whether or not we are alone in the universe. Now, within our solar system, when I say alone in the universe, that basically means finding a microbe elsewhere, or in the most optimistic scenario, some sort of multicellular creature beneath the ice of Europa or Enceladus. But nevertheless, finding life elsewhere in our solar system is an exploration that we can engage in and not be passive, whereas with SETI, we kind of have to just scan the skies with the hope that somebody out there once upon a time sent a signal that we can then catch at this point in time.
What would be funny, and this is very science fiction speculation, but what would be funny is if we did get a radio signal at some point and we were by some miracle able to figure out what it meant, and it's aliens asking if we figured out how abiogenesis happened, and they don't know. Do you think I'm off base with that, though? That to expect within the next 40 years, we should have an answer? Do you think we're on track to actually be able to say if it's hard or it's easy?
So let's see. I think 10 years ago, I said that within the next 20 or so years, we might have an answer. So I agree with you because given everything that's happening with all sorts of projects and things getting shifted to the right on the calendar, I need to revise my dates. And what are we at? It's 2024. So add 40 years to that. We're looking at 2064. I sure hope by 2064 we have explored Mars in great detail and gotten these samples back, explored Europa and Titan and Enceladus, Ganymede and possibly even Callisto, maybe even Ceres and Venus. Our solar system is just an astrobiological playground, and even Pluto is incredibly intriguing from the standpoint of ices and volatiles that it contains. So in my optimistic scenario of many missions to many worlds, I would say by 2064, we could have an answer to this question of whether or not the origin of life is easy or hard, and whether it has arisen on any or many of these other worlds.
I think also with the ice shell moons, let's take Europa as the sort of archetype, that if you can have life arise in that environment, a locked in life, in an oceanic shell world, there has got to be a lot of those in the Milky Way because let's face it, we have how many ice shell moons are suspected in this star system? I think even Oberon is on the table for that. And then you've got Kuiper Belt objects that may have it, and even Pluto, and you mentioned this, and this one's particularly weird, Ceres, an asteroid that may have liquid water. So there is water everywhere, and it's liquid in this star system, and it's just it's a question, it's a function of time and circumstance of the liquid water. So it seems to me that we have a lot of chances, and even more because we don't even know what's in the Kuiper Belt completely yet, right?
Absolutely. Yeah, these ice-covered alien oceans just offer a tremendous amount of real estate that if the origin of life is easy, say at hydrothermal vents, the type of chemical environment that could be prevalent within oceans like Europa and Enceladus, if the origin of life can easily occur on and within those types of worlds, then I think it's off to the races from a biological universe standpoint. Because as you mentioned, not only do you have a ubiquity of these kinds of worlds within our own solar system, but you also potentially have a way for these worlds to serve as capsules going from one solar system to another, maintaining and sustaining ecosystems in the dark by merit of tidal energy and radiogenic decay through periods of tremendous fluctuation that might occur with the light of a star or transiting from one place to another in our galaxy. So it's a whole new ballgame when you consider these alien oceans.
It really is, especially when you consider that an ice shell, that situation, is protective. So it changes the dynamic of needing things like magnetic fields and atmospheres. That sort of starts to fall to the side, and a whole lot of different types of stars, the red dwarfs, the type K, all of it, go pretty strongly on the table, even if they can't support a surface water planet like Earth.
That's right.
And we see that with it's starting to look like TRAPPIST-1. That system, might be an atmosphere stripper, but it doesn't matter if you get an ice shell, right?
Right. Yep.
Now, what are these spots? The leopard spots. What are they made of? What does this chemically look like in this rock?
Yeah. So again, everything is hot off the press and fresh. So I'll just give you the highlights of what we know so far. And that is that it appears that within Cheyava, we're seeing some reduced sulfur minerals. Why is that important? Well, the keystones for life needs liquid water, it needs the elements to build life, and it needs some form of energy to get the business of life done. And for the most part, wherever we look on Mars, everything is oxidized, everything is rusted. And oxidized minerals, if all you have is oxidized minerals, you don't have a chemical or mineralogical gradient that life could have taken advantage of to get the business of life done. And so these leopard spots, so far, the evidence indicates, may well have pyrite, fool's gold, reduced sulfur minerals within them. And further out, we see sulfate. And so we can see what's called a redox gradient, a reductant to oxidant gradient, in part from the fingerprint of these leopard spots, but also beneath the surface, we're seeing this pyrite, this reduced sulfur in the rock, and then sulfate elsewhere. And so that is really important because that gives us a checkbox for chemical energy that could have helped power life at some point in the past on Mars.
And that's interesting because that's not the only recent discovery regarding sulfur compounds on Mars. There's also those crystals, a weird rock that cracked open, and there's, sulfur compounds in a crystalline form there.
Yeah.
Which obviously sulfur is good for life. But more importantly, I think, is phosphorus. And that's in this rock too, right?
That's right. And a good way to think about sulfur. So we see sulfur at hot springs. You go to Yellowstone, a lot of the yellow and the white and the red often has a connection to various forms of sulfur. You go down to the deep sea hydrothermal vents. Sulfur plays a key role in a lot of the various metabolisms of microbial communities at the hydrothermal vents. And so sulfur is a really important element because of the different oxidation states that it can adopt, and then life can kind of use sulfur along with electrons to get the business, the metabolism of life done, converting, say, hydrogen sulfide or reduced sulfide, pyrite, for example, to something like sulfate. Meanwhile, phosphorus is incredibly important just from a fundamental biochemistry standpoint. From when we look at life on Earth, DNA, RNA, ATP, central to the bonding in DNA and central to the energetics of ATP is phosphorus.
And phosphorus, I remember there was some very controversial work years ago regarding arsenic replacing it, but phosphorus seems to be the weak link for life, because if you don't have it and you don't have enough of it available, you're probably not going to get there. And it seems that Mars has it. Mars had the goods as far as phosphorus, right?
Yeah, that's right. And it's phosphorus, strictly speaking, there is quite a bit of phosphorus, but it gets bound up in rocks like apatite. So one way to think of phosphorus is that it's less sort of bioavailable in general. And so you don't find it in great abundance dissolved in water or in the atmosphere. It really kind of is happiest bound up in rocks.
And that's going to be a future problem with Earth because availability of fertilizer.
That's right. That's exactly the right comparison.
Yeah, there are actually two phosphorus problems. Some people say that, well, the galaxy is somewhat spotty in distribution, but there's a bigger phosphorus problem on this planet because we are running low.
Mm-hmm. Yep,
now,
absolutely.
What is next for this rock before a sample return mission? In other words, what can you do with Perseverance to try and glean anything further out of it, or is it maxed out?
So what the team wants to do next is just survey the area more. And we're in the process of doing that. Just taking a look around at some curious morphologies, some curious structures in the surrounding rocks to make sure that we don't miss anything obvious. We have analyzed this particular rock, Cheyava, in great detail. We zapped it with the Sherlock spectrometer and the Pixel X-ray spectrometer. We've gotten quite a good look at it with those instruments, and we successfully collected and cached a core So the team is incredibly excited that all of that went off without a hitch. But before we leave this site, we'll continue to collect more images and use our Mastcam Z and SuperCam instruments to do what's called remote science, where we can still zap rocks and look at the chemistry, but we don't necessarily need to employ the robotic arm to examine the chemistry in detail. And so, yeah, the team is taking a look through every image and making sure that we don't miss something obvious on the ground on Mars as we head out of this valley.
Now, my last question for you is, how is the spacecraft doing? How is the Perseverance rover doing? It has been wildly successful so far, especially with the copter, but how's it going now?
It's working incredibly well. And you may have seen that earlier this year, our instrument, the Sherlock instrument, encountered an anomaly with our dust cover. This is a cover that, as the name indicates, is typically closed when we're not using the spectrometer or the camera that's on that part of the instrument. It's closed to protect us from dust in the atmosphere of Mars and dust storms, etc. So back in January, the mechanism that opens that cover did not respond to the commands that we sent. And our team, along with the rover team, our Sherlock team and the rover team, worked incredibly hard to scrub the data, try and figure out what was going wrong. And eventually we got the cover open. Now we're not closing the cover anymore because that's too much of a liability, but the spectrometers is operating beautifully. It looks like we're not getting much in the way of dust loading, and so that concern is a bit mitigated. But what's interesting there is that, when you're asking about the health of the rover, what are we at? This is the end of July. Just 2 months ago, our team was incredibly stressed about recovering from this anomaly so that we could be ready to do the analyses, the spectroscopic analyses on these rocks at Bright Angel. And the rover, meanwhile, the rover planners, the team that drives the rover, they were encountering all of these rocks on the rim of the river valley. And that was really slowing us down. That really frustrated the rover planners because, normally they can use auto nav and cover 100 meters a day or something like that. But with all of these challenging rocks along the rim of the valley, we were making tens of meters of progress per day. So while that might have been frustrating to the rover planners and the team as a whole, at least on Sherlock, we were breathing a sigh of relief because every little delay in getting down into the valley and onto the Bright Angel rocks, every delay gave us more time to fix the dust cover anomaly. And lo and behold, we got it fixed just in time to collect the spectra that give us some of this evidence for organics in this rock.
Fascinating stuff. Now, before we go, can you give us an overview of Sherlock itself? How does the instrument work?
Yeah, so it's first and foremost, it's got an incredible suite of cameras to look at basically the microscopic scale rocks and at the abrasion sites that the rover arm makes for us once in order to get beneath the surface of the rocks on Mars. So we've got a suite of different cameras, and then the spectrometer is a combined deep UV fluorescence and Raman spectrometer. Raman spectroscopy, that's a scattering effect that when you collect the photons that are scattered in this particular way off a mineral or an organic compound, it tells you about the various vibrational and stretching modes associated with a compound. So, for example, if you think about two carbon atoms linked together, two masses on a spring, vibrating and stretching that spring that connects them. You ding that with some light from a laser, one in every 10 million or so photons will give you a specific photon that corresponds to the Raman scattering. And we carefully collect those. And with those photons, we can discern what bonds exist in a rock or in an organic compound. So Raman spectroscopy is a type of what's called vibrational spectroscopy, where you can get at the structure of something. The deep UV fluorescence tells us about electronic excitation states. So electrons and various shells within a specific element within a compound, the laser excites those electrons to various states. And then upon relaxation, those relaxing electrons provide photons in fluorescence that we can collect. And so the combination of the UV fluorescence and the Raman spectroscopy gives us quite a suite of information about the minerals and any organic compounds within a given sample.
Amazing, just clues, gleaning clues and doing it from an entire, across the solar system. Pretty amazing that we can do this. Amazing times.
Yep.
Dr. Hand, thank you for joining us today. It was amazing, and I look forward to further developments with this rock and the others that may be in that riverbed, because I don't think it's done yet. I'll bet there's all kinds of interesting stuff there. So good luck with it, and I hope you'll come back and update us next time you find another good rock.
My pleasure, and nice talking with you, John.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.